The purpose of this lecture is to understand the meaning of standard deviation and standard error. In brief, standard deviation is a metric of the variability of a random variable. Standard error is a metric of the expected accuracy of an estimate of the mean of a random variable based on taking a finite number of samples of the variable. So that's a mouthful. What I want to do here is to illustrate what those concepts mean based on some simple calculations. So this demonstration is inspired by this paper by Curran-Everett. I'll provide the reference in the description to the video. Curran-Everett uses the software package R to do some calculations, and I encourage you to look at the paper and follow along with his calculations. R is free and you can get it here. I'm going to do something a little bit different and use MATLAB, which is a commercial package for scientific computing. I'll post the MATLAB codes in the comments below. Okay, here are those definitions we just introduced. So these are word definitions, not formal mathematical definitions, but maybe useful ways to think about these concepts intuitively. The Curran-Everett paper asks the question, what does standard error mean? So the author goes on to do a series of calculations on populations of pseudo-random numbers to give us an idea of what that standard error means. So like I said, I'm not going to repeat exactly what he did. I'm going to do something similar. You can look at his paper, and I encourage you to look at his paper to follow along with what he did as well. Okay, so here's the first calculation that I'm going to show you. The first thing is we set a variable n samples equal to 100. That is going to be the number of samples that we are going to draw from a random population. So we use 100 just because it's a nice round number. Next line of code, what we are doing is generating those 100 pseudo-random numbers drawn from a normal Gaussian distribution with a mean of 0 and a variance of 1. So x is a list of numbers sampled from this mean 0 distribution, and that's what this command returns. And here, these are the first few entries of that list of 100 numbers. So some are positive, some are negative. Here are those values. Next, we use a command cumSum, which computes the cumulative sum of the list. The first entry of the cumulative sum is just the first number. Now, the second entry here is 0.2 something minus 0.3 something, or about minus 0.1. So the next entry is the sum of the first three numbers, and on and on and on. So next, we make a list of the numbers 1, 2, 3, 4, etc. So we do that so that we can take the first entry of this list divided by the first entry of this list, and we just get the value x. If we take the second entry here divided by the second entry here, we get the average of the first two values of x. And we can keep going like that. So what we're plotting here is that cumulative sum divided by the number of terms in that sum. So this is a plot of the simulated experiment where we keep making more measurements and averaging all of the measurements together. And so what we have here at the end of the average of 100 samples, and it comes out to something like 0.1 something. So not surprisingly, there tends to be more variability when the number of samples is lower, this side of the graph. Okay? Like I said, the codes, I'll paste the codes down in the comments or in the description of this video, so you can run the codes yourself. If you do that, you'll get a similar trend, but different specific numbers, and that's because there's a random element here to what we're doing. Here's what I get when I execute the same codes again. Same sort of trend, different numbers. If we increase the number of samples, we get a better, that is more accurate, estimate of the mean. Okay, estimate of the mean. What does that mean? And this is what that means. So here we have n sub s samples of the variable. Each one is indicated by x sub I. And we sum up all of our samples and divide by the number of samples. You know how to do that. That's the estimate of the mean. And here, when we take 1,000 samples, we get a pretty close estimate of the expected mean of 0. Remember, here, we are sampling from a distribution with 0 mean, or 0 average. Okay, so now let's go back to having 100 samples. But instead of doing that experiment only once, let's do it 100 times. So that's what these codes do. Just like before, as you average more of your samples together, your estimate of the mean tends to get closer to the expected mean of 0. But there's random variability in how each of the 100 runs comes out. Now we can see something kind of cool. These dashed lines are plus or minus 1 over the square root of the number of samples. So maybe, or hopefully, you're thinking, oh, divide by the square root of n. I've heard of that before. Yes, you have. So here the population standard deviation is 1. The standard error is 1 over the square root of the number of samples. And we can see that 1 over the square root of the number of samples effectively captures the uncertainty or variability in the estimates of the mean. The width of this distribution shrinks with increasing n sub s. Specifically, again, it decreases as 1 over the square root of n sub s. So that is the crux of it. That is why you divide your estimate of the population standard deviation by the square root of the number of samples in order to estimate the uncertainty in your estimate of the mean. But hang on, before we quit, let's look just a little deeper. Let's look at that running estimate of the mean. I'm going to assign a new variable to that, and let's call it E sub m for estimate of the mean. Remember, we have done this experiment 100 times. So what this syntax says is to plot one row of that array that holds all of the values of E sub m. So this is the result of doing the experiment just once, just one time, just like we did a few minutes ago. Now, let's square all those numbers. Why square them? Well, hang on and we'll see. First, you might notice that as expected, all the squares are positive. That's what happens when you square real numbers. Okay, now let's look at all 100 runs of that experiment. The next thing we're going to do is to take the mean of the squared estimates of the mean, and then take the square root of that. Huh? Well, that sounds complicated, but it isn't. So let's see. So to review, we have a bunch of estimates of the mean, estimated based on different numbers of samples. We square all of these estimates, then take the average of those squares. That would be an estimate of the variance. Next, we take the square root of that estimate of the variance. This is the standard deviation of the sampled population, the root of the mean of the square of the estimates of the mean. So what do we get? At number of samples equals 1, the RMS, root mean square, of the data is 1. That is the standard deviation of the population. At number of samples equals 100, the root mean square is 1 divided by the square root of 100, or 0.1. So that's pretty cool that it comes out like that. So if you were to increase the number of runs to 1,000 or 10,000, this curve would get very smooth and follow 1 over the square root of n sub s very closely. So you can do that yourselves with the codes below. So some of you won't be satisfied without a mathematical proof. So here I'll give you what I call a light proof. So remember, we have a random variable x. We're going to use this bracket notation to represent expected value. The expected value of x is the true mean of the population, which here is 0. So the variance is then the expected value of x squared, which is 1 here. So let's take the mean of two samples of x. That is the expected value of 1/2 of x1, the first sample, plus x2, the second sample. The expected value of the mean is 0. Not surprising. What is the expected value of the variance of the estimated mean? Well, we just square what's in here and get the expected value of 1/4 of x1 plus x2 all squared. So we can expand that square and we get 1/4 of the expected value of x1 squared plus 2 times the expected value of x1 times x2 plus the expected value of x2 squared. So the first and the last terms are 1 by definition, because the variance is 1. The middle term is 0 also by definition, and that's the trick. So why is it 0? Well, as long as x1 and x2 are statistically independent, that is not correlated, and they have zero mean, then the expected value of x1 times x2 is 0. And the final result is 1/4 of 1 plus 1, which is 1/2. So for this distribution, 0 mean, variance 1. The variance of the mean estimated from 2 samples is 1/2. It is the variance of the population divided by the number of samples. So more generally, here. And that's it. So we could say that the standard variance of the estimate of the mean decreases by 1 over n. So the standard error of the estimate of the mean is the square root of that. 1 over square root of n.